Hi guys, this is Mr. Rocco again. This is the week of September 21st. I'm going to be posting again 3 videos onto Canvas and a homework assignment that goes with each video. So please watch the videos carefully. Watch them all the way through from start to finish. Rewind, pause, go back if something doesn't make sense. Watch it again and again until it makes sense. And again, these homeworks are due on Friday afternoon by 3 p.m. Okay, so you have to have the homeworks in by 3 p.m. on Friday. And again, I Zoom in the afternoon on Mondays, Tuesdays, Thursdays, and Fridays. And on Wednesdays from 9 to 11 is my office hours. So those are all Zoom sessions. You can come on any of those times for extra help, even if it's for 5-10 minutes just to get some help or to go over some of the concepts if something doesn't make sense, help with the homework, help with the labs, whatever you need help with. And then the in-person time, same thing. When those of you that come to school can use that time for extra help in school. Okay, so this video is going to be about density. Density is a very common concept that you've probably covered over and over again in other grades in middle school. What you're looking at in this picture here, a couple of pictures, this is Chicago over here on the right, and that's showing you only a few of the tops of the really tall buildings in Chicago, and you have a lot of thick fog. And over here, you can barely make out this guy walking through the thick fog. So usually fog is something that you hear that term density. The National Weather Service will issue what's called a dense fog advisory. What does that mean? Dense fog advisory means there's so much fog in a small amount of space. So density has a lot to do with how much of something you have and how much space does it take up. So you're really comparing two things: mass, which is how much of something you have, and the volume, which is how much space something takes up. So density means the average amount of mass, and we're using grams in the metric system, per unit of volume. Volume can be one of 2 units. If you're talking about liquids like water, or oil, or even a soda, you measure in liters or milliliters, right? You go to the store, you can buy a liter of soda, you can buy a 2 liter of soda. So we're talking about milliliters is the unit of volume. If it's liquid, if it's solid, we're talking about centimeters cubed. Because to get the volume, and this you probably remember from other courses, volume, and excuse me again, I'm using the mouse, volume equals length times width times height. So if you have a regular object, let's say a cube, that's a horrible looking cube. No, it's hard to draw, but not bad. So you would take the length of the cube, you would take the width of the cube, and you would take the height of the cube and multiply those together. So they call those regular solids. A regular solid is something you can use a ruler, measure the length, the width, and the height. Liquids are what they call irregular, right? You can't really measure them with a ruler. You would use a graduated cylinder. You'll see that we're going to do a density lab pretty soon. So anyway, when you measure the length, width, height, you're going to measure the height in centimeters, you're going to measure the length in centimeters, you're going to measure the width in centimeters, and then you get centimeters cubed to that third power. So whenever you see cubic centimeters or milliliters, you're talking about volume. So density is comparing mass to volume, how much of something you have in how much space it takes up. Let's say you're in art class and you have a piece of clay right here, and you want to make the clay more dense. So you take that clay and you just squeeze it together and put all this pressure on it and push it together into a smaller clump. So you go from this side, the left, over to now this side on the right, where it's much more concentrated. You've squeezed all that clay together into a much smaller space. So here, you did not take away any clay. You didn't cut it in half. You didn't take away some of the clay and throw it away. You just took the same amount of clay, but you made it more dense because you made it concentrated. You put it into a smaller space. So when you apply pressure, all right, pressure is going to increase the density. Applying pressure to something like clay or to a gas, if you had a gas in a container, in a cylinder, and you squeezed it together, that gas becomes more dense. This is the equation for density. It's a math equation, very simple. Again, you probably covered this in middle school. It's you take an object's mass in grams divided by an object's volume. And again, volume could be cubic centimeters or milliliters. The reference table, let's take a look at that for a second. If you go to the front of your ESRT, your science reference table that I gave you, here's the equation. It's right on the front cover. There's 4 equations that we're going to be covering this year. Eccentricity, which is when we get into astronomy. Gradient, which also is known as slope, right? Rise over run. In this case, it's a change in something over distance. Rate of change, that's coming up real soon. The change in something over time, like driving in a car, how many miles per hour are you traveling? And then here we're talking density. So there's the equation. It's mass divided by volume. Simple equation. Take the mass on the top, divided by the volume on the bottom. So mass over volume, which again, your units, because mass is always measured in grams, and volume again is up here. It could be cubic centimeters or milliliters. Your units will be either grams per cubic centimeter if you're talking about something that's solid, or grams per milliliter if you're talking about a liquid. This triangle, it says copy, I know that, but you don't necessarily have to. It might not be a bad idea to put it on your reference table. This is just a little trick, and again, I don't know if you learned this in middle school, that will help you solve for not only density, but any one of these things. So you have D for density, M for mass, V for volume. You're going to see some problems sometimes where they might not give you the mass, but they give you the density and the volume. So in that case, mass equals density times volume. Or let's say they give you the mass and the density, but you have to solve for the volume. So in that case, the volume equals mass divided by density. So basically what you do is with that triangle to draw it, as you can see, you make your triangle, you break it up into 3 parts. The D always goes in the bottom left corner. The M always goes up top. The V always goes in the bottom right. And the way I try to keep it straight, or I tell students, is, in a year or two, a couple of years, you're going to go to want to get your learner's permit and then eventually get your license, right? Because that's freedom from your parents. Ha ha ha. So you go to the DMV, and when you read a sentence, right, you read from left to right. So you start in the left corner and you go up left to right. So it's DMV. Think of Department of Motor Vehicles, DMV. So when you're looking at this, right, if I had, let's say, this kind of situation, 10 with a line and a 2, you all know that that means to take 10 divided by 2. So that's what this line means right here, divide. So again, if I want density, it's mass divide volume. If I want volume, it's mass divided by density. When you have 2 things next to each other, again, like in math class, if I said, 10 equals, and I would do this, I don't know if they use a dot. You would use an X or maybe a dot like this, right? When they're next to each other side by side. You knew that 5 times 2 equals 10. Same thing in the triangle. D times, this line right here means times V. So if I knew the D density and I knew the volume, I just multiplied the times V to get the mass. So it's D equals M over V. It's V equals M divided by D. And M mass equals D times V. So this little triangle is a good little trick to help you, again, when you know one of the 3 variables. So let's just do a couple examples here. Let's say you have a regular object. Again, regular means you can measure the length, the width, the height. So I've got a length of 4 centimeters. You can see that right here. That's my L. I've got a height of 3 centimeters. I've got a width of 2 centimeters. So the first thing I do is take those 3 numbers and multiply length times width times height to get the volume. So I have 3 times 2, which is 6. 6 times 4 gives me a volume of 24 cubic centimeters, right? 3 centimeters means centimeters to the 3rd power. Then the problem might tell you, here's the mass, or you had to use a scale to find the mass. So in the second half, it says if its mass is 48 grams, what would be its density? So I have the equation, right? D equals M over V. I'm going to plug the mass on the top. So 48 goes on the top. divided by the volume, which was 24 cubic centimeters. 48 divided by 24. I punched that into a calculator, and that gives me 2. But be careful. It's not just 2. You have to put the units. So kids on the Regents will lose credit if they just put 2. A kid will just do this, and they'll say equals 2. And I'll say, you're halfway there. And they're like, what do you mean? You have to put the grams per cubic centimeter. So don't forget the units. You can't just put 2. You have to put G/cm cubed. So you know it's a density value. Let's do another one. Let's say this one, it's another regular solid. The length is 10, so that's my L. The height is 5, that's my H. And my width is 2. I multiply those together, right, to get the volume. So it's going to be 2 times 5 is 10. 10 times 10 is 100. Good. So that's going to be my volume. And again, it's cubic centimeters. This says if the mass was 50. So again, you put it on a scale, or they gave you the number in the problem. Mass is 50. And my density then, I'm going to do D equals M over V. In this case, I'm doing 50 divided by 100. Be careful, because right away it could go 2. I'll say that's if you did 100 over 50 would be 2, right? Because 50 goes into 100 twice. But this is the opposite. You're flipping the 50 and the 100, which means if you simplify that, 50 over 100 is a half. When we write numbers in earth science, most times, there's a few exceptions, but please don't use fractions, use decimals. So you're going to say instead of 1/2, you're going to say 0.5. So stay away from fractions in earth science in this class. Try to use decimals. I know that's a half, but if a kid puts 1 over 2, that's usually not how you're going to write it. They would like to see it written as a decimal, 0.5. Plug it into a calculator. You'll see it comes out 0.5. And again, units, grams per cubic centimeter. Let's say another example. So you have another regular object, and we have a student named Sarah. And Sarah's going to measure the sides of this object, this piece of aluminum, let's say. So she gets a length of 10, she gets a width of 3, and she's got a height of 2. So the first thing she has to do is find the volume, 10 times 2 times 3, and that comes out to be, let's see, 3 times 2 is 6, times 10 would be 60 cubic centimeters. So remember that number. She's got a V, volume, equal to 60 cubic centimeters. Now she puts that object on her TBB, which stands for triple beam balance, or we don't even use those anymore, not in earth science. We use just digital scales. She puts it on the scale. She finds a mass of 120 grams. So she had a volume of 60 cubic centimeters, and she has a mass of 120. She's going to then plug those into the density equation. So she writes down her formula, D equals M over V. She shows her work, which in this case was 120 divided by 60, and then she gets an answer of 2. And again, units, grams per cubic centimeter. Now let's say Sarah decides to take that object. Let me go back to that object for a minute. And oops, went too far. And she decides to take this object and she cuts it in half. Like that. That's a horrible cut. Let's try that again, Mr. Rocco. So we go like this and like that, a little better. So she cuts this thing in half. What's going to happen to the density? Will it go up? Will it go down? Or will it stay the same? So let's see what actually happens. So make your guess, your inference, right? You're going to infer, will the density increase, decrease, or stay the same if she cuts it? Well, in this case, the density actually is going to probably stay the same, or should stay the same, but let's prove it. So the mass, she cuts it in half. The original mass, remember, was 120. But now, because she cuts it in half and takes away half of this, now you only have half the mass. So the new mass is now only 60 grams, right? Half of 120. Her volume. Well, in this case, she cut it in half. That's not going to change the width. It's still going to be 3. It's still going to have a height of 2. But instead of being 10 centimeters long, it's only going to be 5 centimeters long. So in this case, we have to cut that number. So now, 2 times 3 is 6. Excuse me. 6 times 5 is 30. So her mass has been cut in half, and her volume has been cut in half. So when she goes to do the density, calculate the density, it's 60 over 30, which still comes out to be 2. Because she not only took half the mass, she also had half the volume. So her ratio stayed the same. And therefore, cutting the object did not change the density. And it wouldn't matter if Sarah cut this in half like we did here. She could have cut it into thirds, quarters. She could have run it through a shredder and had all little slivers of this piece of aluminum. It wouldn't matter. Every little tiny piece, cutting it into how many pieces, no matter how many pieces, it's still going to keep the density the same. Now, if she had taken that aluminum, put it in a vice grip, and tried to, or a clamp, let's say, right, in shop class or tech, wherever, and squeeze that aluminum together and crushed it and made it smaller, would the density change? Yes, it would, because now she didn't take away, she didn't cut it and remove some, she just squeezed a piece of aluminum in a clamp or in a vise and made it smaller. That's a different situation. Okay. So the size or volume of any piece of material does not affect density. Again, I could have a little tiny cube of aluminum. I could have a bigger cube of aluminum. I could have a bigger cube of aluminum. It doesn't matter. You could have a piece of aluminum the size of the Freedom Tower in Manhattan. As long as it's still aluminum, it's still the same density. Cutting it, I can cut this in half, I can cut it into quarters, I can just keep cutting it and cutting it and cutting it. No matter how many times I cut this thing, it's still going to be the same density. Density won't change. Looking at the Earth also has a layered effect, as many planets do. This actually goes back to the formation of the solar system. And there's a word, it's called differentiation. Differentiation, you hear the word different in the beginning. So what happened to the Earth, as many planets, there are different layers. If you could slice away the Earth in half and look inside, and again, you probably know this from other courses, there's a inner core, that's this white, this yellow is the outer core, this sort of pinkish color is the mantle, and then you have a thin crust. So you have inner core, outer core, mantle, crust, layered by density. The average density of the Earth, this is the average, is 5.5 grams per cubic centimeter. But at the surface, right up here where the crust is in the 2 to 3 range, 2.7. So what must be true then? Well, in order to have an average of 5.5, but up here on the surface, the crust is only 2 to 3, something inside the Earth must be more dense, and that's going to be in the middle at the core. So the core, and again, you might not be aware of this, the core is very, very dense material. It's made of 2 metals, iron and nickel, which are very, very dense, in the 12, 13 range grams per cubic centimeter. And if you go to your Earth Science reference table, not only do they list the planets, we looked at this the other day, I know for those of you that come into school, the planets are listed, their densities. The inner planets, Mercury, Venus, Earth, and Mars, notice the numbers 5, 5.2, 5.5, 3.9 in the 3, 4, 5 range. These are your solid planets. When you get out to the outer planets, Jupiter, Saturn, Uranus, Neptune, they're in the less than 1 and then the 1.1 to 2 range. These are your mostly gas planets, right? These are called your terrestrials. These are called your Jovians. Why did it end up that way? It wasn't just by chance. It had to do with gravity. The sun, being the most massive object in our solar system, gravitational pull, pulled the heavier stuff toward the sun. So the planets that are closest to the sun, that heavy, dense material, the rock and the metal, ended up forming the inner planets. The lighter material, the gases and things, got left further out. So as the solar system formed, the sun was able to pull in closer to it the heavy stuff, left the lighter objects further away from the sun to form the outer gas planets. Now when you looked at the planets, same thing. Let's go to, this is in the reference table. This is the inferred properties of the Earth's interior. What is the Earth look like inside, right? Inferred we just did last week, guessing. They are guessing as to what the inside looks like if you could slice away the Earth and look at a cross-section. Well, right over here on the right-hand side, there's a different color here, and here are your densities. This is the center of the Earth down here. this is the surface of the Earth right here. So you're going from here all the way down to here, and you have your density numbers. The crust, like we said a minute ago, is in the 2 to 3 range. Depends on what crust. If it's continent, it's 2.7 grams per cubic centimeter. Ocean crust is made of basalt, which is a little bit heavier, but it's in the 2 to 3 range, kind of light. You get to the mantle, here's the mantle, and you come over like this, and here's 3 to 5. There's your mantle, getting a little more heavy, right? 2 to 3, and now we're in the 3, 4, 5 range. Then you go to the outer core. Iron and nickel in a liquid state, but it's still iron and nickel. Now you're into the 10, 9.9, 10 to 12 range. And finally, you get to the middle. Let me get rid of some of this. Here's the inner core, which says iron and nickel. And there's your 12 to 13 range. So the numbers go from 2 to 3, 3 to 5, 10 to 12, 13, 12, almost upper 12s to 13. Getting heavier. Again, why did that happen? When planets first formed, they were not solid. Earth was not solid in the beginning, day one. This took thousands, millions of years. The material was in a liquid state. And so what happened is, it's like water and oil. If you took a glass filled with water and then poured oil into that glass slowly, not quickly, slowly, the oil would sit right at the top because oil is less dense than water. And that would layer out like that. Same thing kind of happened with the planets, including Earth. The heavier stuff, the iron and the nickel, sank to the middle. Right? Gravity is a very powerful force. Pulled the heavier material to the center. Left the lighter stuff up here floating at the top. So the heavy stuff sank to the middle, and the light stuff floated at the top, and then everything in between to form this kind of layer cake. So the planets are kind of like a layer cake to a certain aspect, based on density. Okay. Wood. So if you look at different types of wood, now most homes, if you were to take away the sheetrock and you look at the studs that are in the walls, they're made of pine. Your pine wood is not the most dense. It's not the lightest, but it's not the most dense. Pine, or normal 2x4, has a density of about 0.35. So again, if you took a piece of pine and threw it into a pond or a lake, it would float. Water, by the way, has a density of 1.0 grams per cubic centimeter. Or I should say, because it's a liquid, grams per milliliter. So pine would float because anything less dense floats in anything more dense. So 0.35 is less than 1, it would float. Oak is going to float, maybe not as much, right? It's a little bit more dense. It's almost twice the density of pine. Right? If you ever pick up furniture, if you have a piece of furniture made out of pine, not so hard to lift. If you have oak furniture, like an oak bed or oak dresser, it's harder to lift, right? It's got more density to it. 0.60. Still going to float, maybe not way at the tippy top. It might be like slightly under the surface of the water, but it will still float. Your lightest wood out there that I'm aware of is called balsa. Balsa wood, density 0.16. That's about half the density of pine. Extremely light, extremely light. And then your most dense wood is called black ironwood, which makes sense, right? Iron, pretty heavy. So you're not going to find it around Rhinebeck. Southern Florida, the Caribbean, Central America. So you have to go to like Miami down there, the Florida Keys, the Caribbean islands, but they have trees down there. It's called black ironwood. 1.49 grams per cubic centimeter. So that would be like a rock. If you threw a rock in water, most rocks are going to sink. Ironwood would sink because it's 1.49, pretty dense. Last part is factors that affect density. So we'll go over 3 factors here. Temperature. So cold air versus warm air. Think about your house, right? Where's the coldest room in your house? Typically downstairs, right? The basement. If you go in the basement, you have a basement, it's cold down there. Where's your hottest room? Upstairs, right? In the attic. Or if you ever go up in an attic in the summer, it's extremely hot in the attic. Why? When air gets colder, the molecules come closer together. So let's say these are molecules. Draw some circles. And then let's say I make this air. This is just a little box full of air. I make the air temperature in this box colder. These molecules are going to get closer together. So now we'll look at the after picture. The molecules are going to be much closer together, tightly packed. Again, remember, density has to do with how much space something takes up. So if you pack together those air molecules, just like when you squeeze the clay together, you made the air more dense. What does more dense do? Well, things that are more dense, heavier, what do? They sink. That's why it's cold in your basement or downstairs. The opposite is warm air, right? If you take warm air and you, let's say again, let me draw a box. Let's say you got some air molecules in here, and then you make the air warmer. You make it hotter inside that box. Well, now we look at the after picture. The molecules have spread out. They're much further away from each other. These went this way, these went this way. Everything spreads out. Well, now that it's taking up more space, it's less dense. You stretched it out. So temperature is a big factor. This is like, this is weather 101 right here. Cold air, more dense. Warm air, less dense. And I have a video to show you in a minute, but let me do the other factors here, and then we'll go through that little video. Pressure. We talked about that, right, when you take the clay. So if you squeeze together the clay, right, and you make it take up less space, you're pushing it together. You didn't cut it. You didn't rip it some away. You kept the same amount. You didn't change the mass. You just increased the pressure on it. You're making it much more dense, more concentrated. When we get into weather, that's a big factor. There's what they call high pressures. You look on a weather map and you will see a big, and this will happen in the winter time, or this time of year too. Anytime you'll see a high pressure, you see an H. A high pressure is a colder air mass or cooler air mass, which is what we have right now. This weekend, if you notice, it's been pretty cold at night. Today was probably in the 60s, I think, low 60s at best. Nighttime, we got some frost. That's because it's cold air. It's high pressure. So high pressure will cause colder weather. The opposite is the warm air. So warm air, when it spreads out, the air is going to move, it's going to expand, it's going to go outward. That's going to create low pressure. So cold air is high, warm air is low pressure. And then the last factor is what phase, right? Typically, solids tend to be the most dense. Why? Because you're pushing, the molecules are closely packed together. You take a piece of wood or a piece of iron, metal, the atoms inside that wood or inside that metal are closely packed together. That's going to make it more dense. Gases tend to be the least dense, right? Because the molecules are spread apart from one another. And again, less dense, less packed, less density. And then your liquids tend to be in the middle. Right, so most dense solid, least dense gas, liquids in the middle, with the exception of water. Water, which is a very unusual, it's just an amazing substance. I know it's just water, Mr. Rocco. It means totally different situation. Water, think about a pond. When in the wintertime, when that pond freezes, right, where does the ice sit? Well, it floats on top, but yet it's solid, right? Most things I just said a minute ago, solids tend to be the most dense. Except water. Water, when you freeze it, it doesn't compact. Most things, when you freeze them, they get closer together, like you see up here. Water does not compact. Water molecules actually expand and makes the ice less dense. That's why when you take ice, an ice cube, let's say, put it in water, it floats, right? Less dense float. So water is the exception to the rule. Again, most things when they're solid tend to be more dense, except water. Water is more dense when it's in the liquid phase, not the solid phase. All right, let me show you this quick little video. It's on YouTube. Hopefully you'll be able to hear it. I'm going to mute my mic, play this video about density, and then this will be video number 1 for this week. So let me get this video up and running.
Density facts. A can of Diet Cola will float, and a can of regular cola will sink when placed in water. You see, in the same amount of fluid ounces, there are more atoms in the can of regular cola. The main ingredients in cola are carbonated water and sugar. So each can has the same amount of water molecules, but in the same space, the regular cola has additional molecules from the sugar. Putting more atoms in the water forces the molecules to be more dense, making the cola sink. Hot air balloons fly because of density. Just like all matter, air is made up of atoms and molecules. When air inside the balloon is heated, it expands or gets bigger. So compared to the air around the balloon, The atoms inside have more room to move around and, as a result, are not as tightly packed together. The air inside the balloon is less dense than the surrounding air, and the balloon becomes buoyant. When it's time to land, the pilot stops heating the air, and as it cools, it contracts to match the density of the surrounding air. The effects of gravity go to work and bring the balloon down to Earth. If an object is cut in half, its density remains the same. Take a look at a gold coin, made of neatly arranged gold atoms. When cut in half, the tightness of the atoms does not change. Whether you have a half of a coin or a complete gold coin, the density stays the same. The density of liquid water is 1. Objects with a density of less than 1 will float, and objects with a density greater than 1 will sink. Take a look at these 3 objects. All of them float, so their densities are less than 1. But if you take a closer look, you see that as density increases, more of the block is below the waterline. Scientists have figured out the density of a block converted to a percentage is equal to the amount below the waterline. For example, if 75% of a block is below the waterline, its density is 0.75. Ice floats because of density. When water freezes, it expands. Just like the expanding air in the hot air balloon, water molecules in expanding ice spread further apart. The atoms in ice are not as tightly packed together as they are in the liquid phase. If we observe an iceberg, notice about 92% of the iceberg is below the waterline. This means that the density of ice is 0.92. Density facts. To learn how to measure the density of water, click Density of Water. To see a collection of all science videos, click All Videos.
Okay, and that is it for video number 1. Again, watch the whole video, go back, rewind if you're stuck, and don't forget, I will now I'm gonna post 2 more videos for the week. So video 2, video 3. Make sure you watch all 3 and work on those homeworks. Okay, I'll talk to you soon. Bye.